Okay, in the last video, we talked a little bit about parametric equations, and we used the chain rule in this particular example to get an expression for dy dx, where x is expressed as a function of t and y is expressed as a function of t. And from this information, we could easily enough find out what dx dt is, and we could find out easily enough what dy dt is. And then to determine dy dx, we had to use the chain rule. dy dx is equal to dy dt times dt dx. If you think of multiplying these together, where the dt's cancel out, and you have dy dx. And when we did that, we had this answer here minus the cotangent of omega t in parametric form, and then converting that back to x and y, that's the same thing as minus x over y. Now what we want to do is we want to find the second derivative. And we'll do it first of all then by taking the derivative of this. Then we'll work with the parametric equation and see if we can get an expression for d squared y dx squared, and then see if it's the same as what we get originally. So let's see, we want to get d squared y dx squared, our second derivative. And of course that's d dx of dy dx. The second derivative, of course, is the derivative of dy dx. So this will be equal to d dx of minus, and I'm going to write this as y to the minus 1 times x. And we need to take the derivative of this quantity here with respect to x. So let's see. This would be, we have this times the derivative of this plus this times the derivative of this. Let's write it down here. So this will be equal to, we will have this times the derivative of this, so we have minus y to the minus 1, and the derivative of this is just 1. It's going to be dx dx, like this, which you don't bother usually to write down because that's just 1. So we have that, then we're going to have plus x times the derivative of this. And that's going to be, take the minus 1 down from here. We're going to have minus 1 times minus 1, so it will be plus, and then we'll have times y to the minus 2 power. The new exponent is going to be negative 1 minus 1. Negative 1 plus negative 1 is negative 2. But it's going to be y to the minus 2 times dy dx. And what is dy dx? That's this. So this will equal minus 1 over y, and then we're going to have x to the y over 2 times dy dx, and that's a negative sign. So that's going to make this minus this quantity times x over y. So let's see what this takes us to. This will be equal to minus 1 over y minus, and here we have x squared, and also x squared over y. And that is squared y dy squared. Minus 1 over y minus x squared over y. We could probably manipulate this though, because let's go back to here at how x and y are written. X squared is what we have here. X squared is the cosine squared of omega t, and cosine squared of omega t is the same thing as 1 minus the sine squared of omega t, which is 1 minus y squared. So x squared equals 1 minus y squared. So we can substitute that up here. This will equal 1 minus y squared. And this is 1 over y squared times y, so this should be y cubed. We had x squared over y cubed, and x squared is 1 minus y squared. Okay, so let's see how this is going to work out. We have this will equal minus 1 over y minus 1 over y cubed plus y squared divided by y cubed. That's going to be 1 over y. And these cancel, so we get the square of y dx squared equals minus 1 over y cubed. And that we got from using this. Okay. Now, suppose that for some reason we had dy dx like this, and we did not want to use this to determine d squared y dx squared. So here, d squared y dx squared, of course that's d dx of dy dx, and that's equal to d dx of minus the cotangent of omega t. And here's where we use the chain rule. This right here is a function of t. We want to take the derivative of this whole function here with respect to x. So that would be equal to the derivative of that function with respect to t times dt dx. And again, like up here, you can think of these dt's canceling each other. So you have a dy dx. Here you can think of these dt's canceling each other. So I have a d minus cosine of omega t with respect to x. So let's move along here then. What is the derivative of this with respect to t? The derivative of the cotangent is minus the cosecant squared, and we have a minus sign here, so that gives a plus cosecant squared of omega t. Then we'll take the derivative of what's inside here, which would be omega times dt dt, which is just 1. So we have omega here. Then we have to multiply by dt dx. Now I have to go back up to here. dx dt is this, so dt dx is going to be 1 over that. So we have minus omega times the sine of omega t. And that is d squared y dx squared. These cancel, and this will equal minus Now the cosecant squared, that's 1 over the sine squared. That brings it down to here where we already have a sine, so this will equal minus 1 over sine cubed of omega t. And then we go back up to here. The sine of omega t is y, so it equals minus 1 over y cubed. So you can see that determining the second derivative really seemed like a simpler chore when we work with the parametric equation. The part right here, though, that we want to pay attention to is this, because this is where we use the chain rule. This is a function of t, and taking the derivative of that function with respect to x, that's the same thing as taking the derivative of the function with respect to t times dt dx. Same thing as what we did up here to get dx dy. Here we had dy dt times dt dx. You think of those canceling out, so we have dy dx. Here you can think of the dt's canceling out, so you have d minus cosine omega t with respect to dx. So this is how the chain rule comes into play. Once we do that, then the rest of the problem pretty much falls right into place. So that's it for this video. Come back and join us for some other videos, and we'll continue practicing the chain rule here for parametric type equations.